Okay, welcome to lesson 7 of our second unit. So we're getting close to the end, 2 more after this. Yesterday's lesson, or the previous lesson, looked at graphing to combine functions. Today we're going to do it algebraically. So stepping away from the graphing again for a little bit, which some people might be celebrating and other people might be like, oh, I like graphing. So I apologize. That's why we do it both ways, so that you have kind of both pieces. Whether you like one or the other better is kind of up to you, but you need to be well versed in both for math. So just a quick recap here. You're given a function and you're asked to find specific values. In this notation, function notation, again, we're told that this is our input, this is our x value. And so when we're going to deal with this, that's basically what we need to remember, is that that value is then going in place of x wherever we see it in our original function. So I'll do the first one real quick with all the steps, and then I would encourage you to pause the video either before even the first one or after you've watched that quick example for the first one, and try the second two on your own. So I'm going to plug in 2 to my equation. So 4 times 2 plus 5, 2 squared. So that's 3 minus 8 plus 4 times 5 is 20. So that's going to be negative 5, positive 20 is 15. Okay, so that's how I would evaluate these. Try the next 2 on your own. So the nice thing about 0 is it basically just takes out those 2 terms that have x in them. So that made the second one pretty simple. The third one, just watch out for that negative. It gets put in, and squaring it makes it positive. So it doesn't change the sign of our 5. So let's take a look at these notations. So we're given our 2 functions. We're given f of x, and we're given g of x, and we're asked to do a bunch of different things with them. So some, we're going to see it written like this. You could also see it potentially written as f plus g of x. Okay, either notation is going to be totally fine. I'm going to switch my colors out actually. So I'm going to go with orange for f and pink for g, so we can kind of differentiate, at least to start with. So I'm going to write them out individually, and I'm going to plug in, instead of f of x, now I'm going to write in the actual function. So 2x plus 3 plus negative x plus 2. So if I'm adding them, I don't really necessarily need the brackets. From here, I'm going to combine like terms, so x's go together. 2 minus 1 is x. 3 plus another 2 is positive 5. So my f plus g of x, if I want to write it like that, my sum of these 2 functions simplifies to just be x plus 5. If I'm subtracting, I'm going to go, sorry about that, 2x plus 3 minus negative x plus 2. Now remember, if we're subtracting, that extra negative just, it basically implies opposite. So I can go through and just change all my signs. What's going on here? So now I've got 2x, and another one is 3x. 3 minus 2 is positive 1, so that would be f minus g. So again, either notation is perfectly acceptable, whether we show it as this way, as subtracting each individual function, or subtracting the function names. Both work, so just be aware of that notation difference and the fact that they mean the same thing. F times g of x, well, we're doing the same idea. So we've got 2x plus 3. This time we're multiplying, product again, meaning multiplying, by negative x plus 2. Because we're dealing with 2 binomials, that means we're going to use FOIL. So if you've forgotten that from like grade 10, it's firsts, outsides, insides, lasts. So that gives me negative 2x squared plus 4x minus 3x plus 6. These middle terms both are single x's, so I can combine them further. And that would be my final answer. And again, we could note this as f times g of x. Now this notation is going to be less common, strictly because we're going to come across a different way of composing functions that's going to look very, very similar. It's f of g. So you can see how the similarities are there. So I'm not going to be using this notation. I'll definitely default to this one here. But again, that's up to you. This means something completely different. Finally, quotient-wise, we would just write our functions in again. 2x plus 3 divided by negative x plus 2. At this point, we would also need to define any non-permissible values, because we've got a denominator and denominators cannot be 0. So negative x plus 2 cannot equal 0. So x cannot be positive 2. Okay, so when we get into quotients, you will always need to worry about non-permissible values. So I apologize, I didn't realize that this had broken up this example. You've given two functions. If we added them, find the value for each. So we are working a little bit with graphs here still. If we were working with a new function, f of x plus g of x, what is it when we're dealing with x equals 2? So we could say h of 2 equals f of 2 plus g of 2, in which case we just need to define those points. So I'd say that this output was 2, that's my y value, versus negative 1. So my final answer would just be 1. Okay, if I was subtracting, and it just so happens I'm working with the same x value, so d of 2, I'm going to jump right to my output. So 2 minus negative 1, so that would be 3. If I was multiplying with the same x value, that would be 2 times negative 1, be negative 2. Okay, so that's how we would do it graphically. Just kind of as a quick note, recap of yesterday. Okay, example 2, if f of x is the square root of x and g of x is x minus 3, state the domain of each one. So working with f of x, my domain, well, I can't take the square root of a negative number. We know that that's a restriction, so it can't be less than 0. So we're starting at 0. 0 is allowed to have us take the square root of it, and it would go forever in the positive direction. Any positive number can have the square root of it taken. My range then would also be starting at 0, because the square root of 0 is 0, and would extend to positive infinity. Now, if you remember what the graph looks like very vaguely, it kind of looks like this. It looks like it plateaus. It's just very slowly increasing, but it is still increasing, so I can still say positive infinity. For g of x, my domain could be anything. There's no restrictions on a linear relation or function. So it can be negative infinity to positive infinity. My range would also be negative infinity to positive infinity. That is supposed to be a rounded bracket. Write an explicit equation for h of x, given if we're adding them. So if we're just adding them, then we could literally just write it as this plus this minus this. Okay, so remember f of x, g of x Okay, and because we had that restriction with the square root, that restriction unfortunately doesn't go away. So our domain would still have to be restricted, even though for g of x it wasn't. But because for f of x it was, we still need to maintain that. So my domain would still be from 0 to infinity. My range, on the other hand, might be a little bit different. Okay, so this might shift it downward a little bit. Okay, using graphing technology would be your best option, just so that we can acknowledge that this has changed. So if I enter my equation on Desmos, this is the graph that shows up. So we still see that defined x cannot be less than 0, but like we saw, and we saw it in earlier in this unit for transformations, that -3, that constant at the end, is impacting where my graph is starting. So whereas my range in my original square root function is starting at 0 and increasing upward that way, here we're going to see that this ends up becoming more linear. It increases much faster than a regular square root graph, but we still start at -3, like the transformation would imply. So my range here would be from -3 to positive infinity. Okay, so restrictions on the domain apply to new functions as well. If we were multiplying, we would have the square root of x times x minus 3, which would be x root x minus 3 root x. It's another way of thinking about it. We still have the restriction where under the square root sign, we cannot have a negative number. So we still have to start at 0 and go to infinity. Now, in terms of other implications of this, in terms of like, say, my minimum value, well, I know that I need to start at 0. So if I don't have graphing technology at my disposal, I can also check for where would my range start by actually plugging it in. So at p, when the function when x equals 0 would be 0 square root 0 minus 3 times the square root of 0. Well, that all ends up being 0. So for my range, my starting point will be back to 0, just like before. Now, we've got our last video, or last example for this one, would be d of x is when we're dividing. So d of x is the square root of x divided by x minus 3. So here, we already know that there's a restriction that x has to be greater than or equal to 0. But here, we also know that x minus 3 cannot be 0. So x cannot be positive 3. So we have both a restriction on our domain plus another non-permissible value. So what does that mean? Well, it means we're going to get a pretty trippy looking graph. We need to kind of bear this in mind for when we write our domain and write its domain, and we could even figure out its range. Well, we're only worried about domain here. So with these restrictions, my domain then would be from 0 to positive 3, but because it's a non-permissible value and we're dealing with a reciprocal function, I know that that's an asymptote. Okay, going back to my grade 11 learning. And so my graph will pick up on the other side of 3 and continue to positive infinity like it would have if it was just a square root graph. Now, if you're not familiar with it and you wanted to test some values, you're more than welcome to. If you want to jump back and use technology to double check this, you're more than welcome to. You won't have that luxury on the exam. So that's why it's good to really be able to recognize that, like, this is although it's a radical function, it's also a rational function, and rational functions have asymptotes. But just to prove it to you, let's go here and I will create the graph. And so here we go. This is what we're seeing. We start at 0. We can't go left of 0 because of that restriction in our radical, but we can't actually have a point defined at 3 because of our denominator. And then again, it picks up here. So that's kind of how our graph works. If we wanted to talk about range, we would then talk about, it would go from -infinity to 0, a defined point at 0, but then it would pick up on the other side of 0 and never actually equal. So I'll write it out for you. It's a really weird one, but just FYI, as a little extra, our range would be from -infinity, which is new in comparison to our other ones, to 0. And we had that defined point at 0, 0. So I'm going to use a square bracket. But when I picked up on the other side, on the positive side of 0, it's behaves like an asymptote. So I'm going to use a round bracket and say from 0 and extending upward to positive infinity. So that's a really weird range. I wouldn't have expected you to necessarily identify, especially the square bracket piece. That's a really tricky one to spot. But the domain should be a little bit more manageable based on what we know about each of these individual functions. So the new domain is restricted to those values for x which the function in the denominator does not equal 0. And so this is basically what's coming from our non-permissible value. Okay. And we still have to use the functions like in where they are defined originally based on our original domain. So example 3, it's kind of nice. They've both got relatively reasonable domains and ranges. So for f of x, it's a linear relation again. So I've got some very flexible domain and range of -infinity to positive infinity for both. Okay, for g of x, it's relatively simple. Just remembering that absolute values are never negative, so we're going to have a problem with our range. Domain, there's nothing we're not allowed to put into an absolute value. So -infinity to positive infinity are good to go. Range just means it has to be positive, so starting at 0 and extending forever in the positive direction. Write the equation for f of x minus g of x. So h of x equals x plus 2 minus the absolute value of x. What does this mean? Well, it means that we're going to throw in this piece where our absolute value is actually reflected downward. And so that might make some weird changes, but we're always going to be subtracting a positive number from our x value. So if we wanted to rewrite that just to kind of wrap our heads around it, it still kind of looks like a linear equation. We're going to have some funky stuff going on. So you can create a table of values if you wanted. Because I have the option of using technology, that's what I'm going to do. So I'm going to be going into decimals and testing this one out. If I had to make a prediction before I actually graphed it though, because I'm dealing with absolute values with that subtraction sign in front, I'm going to say that my range might be affected and that I might not ever have a positive graph. And that also goes with the 2 influencing my transformation. It's going to shift it downward. So I'm going to pause the video just to do this. Sorry, I said it would be shifted downward, but it shifted upward because it's +2. That was my mistake, just thinking it was subtracting 2. Okay, so we see that steep line that I probably would have expected for my absolute value / linear equation. What's weird is that once we hit positive numbers, we're actually canceling each other out. So they're just staying flat at 2. So I do have a maximum, but unlike a regular absolute value graph that reflects back down, this one kind of plateaus. And that makes sense based on what you see in our equation. So we see if this is positive, like for example, h of 3, Well, that would be 3 minus the absolute value of 3 plus 2. Well, all of this equals 0. So we're just left with positive 2, and that would work with any positive number. Whereas if we work with negative 3, that would be negative 3 minus the absolute value of negative 3 plus 2. Well, that means the absolute value of negative 3 is 3. So it's negative 3, subtract 3 more is negative 6 plus 2. So that's where we get the variation in values, as opposed to plateauing in positives. Once we've kind of established that that might be a pattern, that's where we kind of have the red flag, positive versus negative. And again, that's hinted at with an absolute value graph. Now we can establish our no domain. There's still no restrictions because our original graphs didn't have any restrictions. We don't have a denominator now. So nothing's really changed. So x-wise, we're still good to go. It's that range that really got altered. So whereas before we had a minimum that was restricted for our absolute value, because we threw that negative out in front of it and we subtracted it, now we've got a maximum. So our negative infinity is going to exist, and that maximum, as we saw in the graph, was 2. Again, you could totally figure this out by using a table of values. Just be smart about which values you're choosing. I would have definitely chosen both positive and negative numbers because of that absolute value. I'd want to see like how that influenced my output, and just being conscious of that, again, transformation piece happening with this plus 2 at the end. For multiplying, I'm just gotta go back and check my function. So I've got p of x, so x plus 2 times the absolute value of x. So it's going to be x times the absolute value of x plus 2 times the absolute value of x. So this is going to be like a quadratic equation. But we're going to get some negative numbers, so it may end up looking a little bit like a cubic. Where all of a sudden, when I put in a negative value, so like negative 3, I'm going to have negative 3 times the absolute value of negative 3 plus 2 times the absolute value of negative 3. So this is going to be negative 3 times positive 3 is negative 9 plus 2 times the absolute value of negative 3, which is positive 3. So that's going to be 6. So I'm going to make a table of values for this. You are encouraged to do the same so you can determine your domain and range. Again, be smart about which values you choose. The second we're working with absolute values, you want to work with positives and negatives. Okay, so whereas we saw a plateau happen in our add addition graph, we actually find that we don't have the same thing happening here. If you want to double check, you can always use Desmos, but again, getting more confidence in your table of value making and in your choosing of appropriate X values is definitely a skill you want to consider when looking at domain and range. So again, and going in and checking on Desmos doesn't hurt. This is what our graph would look like. So again, we're seeing we've got like a local maximum, but then our graph continues going upward. And that was what we saw from our table of values as well. It continued upward, it continued downward. So when I go to do my domain, again, it still doesn't have any restrictions, just like my original functions. My range now also doesn't have any restrictions. So it's more domain than range that is influenced by the original functions. Range can vary depending on how we actually assemble them and what operation we're doing, whether it's product, quotient, summation or addition, or subtraction. So the last one is f of x divided by g of x. So when we're dealing with this function, we've got x plus 2 divided by the absolute value of x, remembering that the absolute value of x cannot be 0, so x cannot be 0. This is a non-permissible value. So when I go to write my domain, now I'm acutely, and I check the numerator, but there's no restrictions there. So my only restriction is this non-permissible value. So it's going to be from negative infinity to 0, united with 0 to positive infinity, just not including 0. Again, if you're defaulting to that set notation, this would be written as x is an element of the reals, but x cannot be 0. Whichever you prefer. Alrighty, so we've got example 5 and example, or 4 and 5, and then we're done. So stick with me, we're almost through this lesson. If we consider h of x, and we know that it's 3 explicit functions that we're adding together, so f, g, and h, or f, g, and d combined so that we made h, I would want to do this as simple as possible. So I would say maybe f of x is x squared, g of x is negative 2x, and d of x is just negative 3. That would be the absolute simplest way of doing this. You could choose anything. You could get all sorts of complicated. You could have 3 quadratic equations that somehow added to make h of x, but I'm going to keep it simple. So I would have to write 2 explicit equations for if I was subtracting f of x from g of x to make, again, this new function. So I could do something like f of x could be still x squared, and then g of x could be 2x plus 3. And the reason that I switched the signs there is because we're subtracting it, so we would have had to distribute that negative through to both. The trickiest one is going to be this C part where we have to come up with functions that multiply together. So this is where factoring might not be a bad idea. So noting that the factors of this are x minus 3 and x plus 1. Being quick at factoring is going to be an advantage in this unit and in our polynomial unit. So just a heads up on that one. Start practicing your factoring if you've gotten a little rusty. But f of x, so once I've factored it, f of x could easily be one of those 2 factors, and g of x could be the other. So that's kind of how I would tackle that question. Again, I'm going to shoot to try and make it as easy as possible for myself so that I just don't have to think too hard about this, because the second we start talking about like, oh, well, what if it was f of x is like x squared minus 3x plus 3. So then g of x could have been just positive x to make that more positive by 1. And d of x could have been negative 6 then to bring that constant down. All of a sudden, I'm just starting to create more work for myself. So if I don't have to, I'm not going to, but this technically would be a correct answer as well. So there's no one right answer. There just is some that are a little bit simpler than others. Our last example is given q of x is x plus 1. Write explicit equations for 2 functions f of x and g of x that produce this. So this is probably the trickiest type of question to deal with. I would say that the easiest answer would be I would say the easiest answer would be that f of x is x plus 1 and g of x is 1. That would be your quickest solution. Conversely, if you want to make it just a little bit less on the nose, you could say f of x is negative x minus 1 and g of x is negative 1. That would also work. If you wanted to start getting into some serious algebra, you could go along the lines of x squared minus 1 divided by x minus 1, because now I'm dealing with a perfect square. So this would be x plus 1, x minus 1, or a difference of squares rather, divided by x minus 1, and we would cancel that out. The only problem with this as an option is that it would have to have a restriction in the domain of x cannot be 1, and we're not told that for Q, so this technically is not your best answer. Don't do that. Go with these instead, where we don't have that variable in the denominator making further restrictions on our domain. So that's this lesson. I know it's a little tricky. Again, we've got some practice questions after the next unit or next lesson. I'm going to try to find more practice questions just explicitly with algebraic equations, but the next lesson looks at doing what's called composite functions, f of g of x. So instead of just adding, subtracting, multiplying, or dividing, we're going to be putting functions inside functions. And unfortunately, most of the worksheets I've been coming across so far have included this in it. So you could easily start the homework that's listed after lesson 8, because you see a lot of adding, multiplying, subtracting, etc. It's just that you will come across some composite functions as well. And so I didn't include them until after that. But feel free to do like the first page of 8.2. Absolutely. Maybe a little bit less so on the 8.1 front. Okay, so give those a shot. If you have any questions, like always, please, please, please contact me in some way, shape, or form. And otherwise, lesson 8 should get posted really soon.